Okay, thanks very much. So hi, and a very good afternoon from my side. First of all, I want to apologize that I cannot be there with you in person today. And my special thanks goes to the organizers and to the chairs, which made it possible that I can present remotely. The topic is authenticated key exchanges, particularly in a large-scale quantum-safe setting. And this is joint work with Sonja Bruckner and Sebastian Ramacher. And authenticated key exchanges are one of the most interesting or important protocols, let's say, we use today. And particularly having the large-scale quantum-safe networks in mind, key exchange can be built from primitives that are currently under standardization from NIST, for example, and this gained a massive interest. But not only NIST, also the German BSI, the Federal Office for Information Security, pushes the post-quantum cryptography as a building block, and as well as the French ANSI in that regard. On the other side, key exchanges can also be built from other primitives, particularly also it's known that can be built on so-called quantum key distribution, which is QKD. QKD can also be used for key exchange, which in an ideal setting offers even information theoretic security, while post-quantum security relies on computational assumptions. There's also gained some interest in the European Commission, obviously, in 2019, sending the future as quantum, then the EU countries planned an ultra-secure communication network, particularly basing this network on QKD. And then shortly after, the European Quantum Communication Infrastructure Initiative, short the EuroQCI initiative, was elaborated to design, develop, and deploy the EuroQCI between all 27 EU member states. And this is particularly also seen as an integral part of the IRIS-2, which is the new EU space-based secure communication systems. I want to, as a disclaimer, I want to say that in this talk, I do not want to promote any of the primitives, either post-quantum crypto or QKD. There are many more experts out there. But as a cryptographer, I'm particularly interested also on a higher level, which is that distributing trust in quantum-safe networks is the thing, particularly going to the topic of do not pull all your eggs in one basket. Meaning, as cryptographers, we're interested in large-scale quantum-safe networks, with the best resilience, let's say. And this, as it turns out, there's a hybridization approach, which comes in particularly handy, combining the PQC and the QKD. And this will be essentially the central topics of this talk. Since probably most of you know post-quantum cryptography, I will start to recall quantum key distribution, or establishing a shared key with perfect secrecy. So in the most basic setting, you see it here on the right, there's the site A and the site B, which are directly connected. There's some key management entity A, key management entity B, which is connected by a classic channel and a quantum channel. And the main features here are that they can perfectly distribute a secret key. This can be between any two endpoints that are directly connected, can be via terrestrially or via space. And when you go further to build QKD networks, there are particularly gaps to solve. You see it here on the right. There are site A, site B, and site C. Site A wants to connect to site C, but since there's a particular range limit within QKD, depending on the technology and the desired key rates, it might be 100 kilometers or something in that range. There must be a site co-located between site A and site C. This is site B in this example, and which must be a trusted node. So site A is connected to site B, and site B is connected to site C, and each has their QKD devices included. So we need, for QKD, trusted nodes to bridge longer distances, and even more, you need pre-shared keys to authenticate link-to-link nodes. That means if site A and site B if site A and site B want to talk to each other, they do a mutual authentication based on pre-shared keys. The same thing happens with site B and site C. This limit has been acknowledged also in the literature and are quite well known. I want to quote here first on the authentication. This is taken from the paper you see on the right, that QKD is a solution for transforming a non-confidential authenticated channel into a confidential authenticated one. Yeah, which means that authentication is already an assumption you have to make before starting with QKD. The second one is the trusted nodes, that they are needed for longer range QKD, and indeed this is also backed by the work on long range QKD without trusted nodes is not possible. Current technology, where they also looked at current technology, particularly a patent, which claimed that long range QKD is indeed possible without trusted node, but it turns out not so easy and does not seem to hold. So it seems that we are stuck with trusted nodes for long-range QKD. So let's go a little bit deeper into the limits. I will start with end-to-end authenticity, particularly for large-scale QKD networks. You see here on the right, QKD network, which 6 entities, and the entities want to talk to each other. As we've learned, the authentication is done via pre-shared keys, and this is only link-to-link. Each device is only mutually authenticated. Each neighboring devices are mutually authenticated to each other, but not the entities are end-to-end authenticated. And the reason is that Authenticated is not transitive, and for QKD you want to retain the information theoretic security. That's why you are essentially using the pre-shared keys, and you want to do that. There is one solution. You can deploy unique pre-shared keys for each entity. However, this results in a big O of n squared pre-shared keys for n entities, right? So each entity authenticates to each other, needs that particular pre-shared key. And this is done via an offline key exchange, usually via trusted courier, which goes around essentially and with speedy devices, something like this, and puts out the pre-shared keys. Particularly, this is an interesting setting. What happens actually if the entity is changing in the more dynamic setting? If an entity changes, you have to distribute the pre-shared keys again. This might be manageable, yeah, right, on a QKD basis or for smaller networks, but it gets rather inefficient when the network gets larger, particularly looking at the EuroQCI, which there are several nodes available that are connected to each other. The second limit on the trusted nodes is that since it's called trusted node, the trusted nodes between two sites, here site on the right, site A and site B, and the path between them, the trusted nodes learn the secret keys or learn the secrets. That's why they need to be trusted. But what happens in the case it's compromised, and indeed here the solution can be hybridization. That can be combine the QKD part with the post-quantum secure mechanism. And indeed this works, but it establishes end-to-end security. Albeit you have to rely on computational assumptions for that. The hybridization was researched already, and there's a term called hybrid authenticated key exchange. I know that there in the literature currently there are different meanings for hybrid, and for this talk or this work particularly I stick to combining PQC, QKD, or maybe also classical. And this was, as said, this was not coined by us, it was coined by prior work, and we stick to that here. So how do these hybrid authenticated key exchanges work, or HAKE for short? I want to define it in a clean way on a cryptographic level. Their main features, these are the session-based protocol between any two entities that send messages back and forth, and with the result that an authenticated shared key is established. The goals that we have here is that authenticity of both entities is guaranteed, confidentiality of exchange messages are given, and moreover, the desired security features are forward and post-compromise security. I will go into detail on one slide later, but just keep in mind that these security features are essentially state-of-the-art now for key exchange protocols. You can do authentication as well, set that the method with pre-shared keys, but you can also do it with certificates or passwords. And the ephemeral keys, ephemeral is the term here used because it's related to the session-based paradigm, can be established by a key encapsulation mechanism and QKD keys. And there's a particular hybrid authenticated key instantiation called Muckle. This was presented and published in this particular conference in 2020 with the title of Many a Mickle Makes a Muckle, with essentially saying many small things can add up to larger amounts. And it's done by Dowling, Brandt Hansen, and Kenny Patterson. And essentially, they do what the title is saying. They're combining keys from the QKD layer, combining keys from the key encapsulation mechanism, and optionally keys from the classical cryptography. And for authentication, they use pre-shared keys. The benefits you get is that you achieve end-to-end authentication and confidentiality relying on pre-shared keys, okay? The strong security guarantees, forward and post-compromise security, meaning, as an example here, if PQC should fail, guarantees for QKD still hold. The other way around, of course, as well. If QKD fails or is not available, the PQC guarantees hold for order in your session. And also, there's a particularly backwards compatibility feature here, which is essentially saying that the protocol adds a QKD PQC layer to existing classical one. That's particularly interesting for migrating to quantum-safe systems. You see here depicted on the right, essentially in a very basic form, that the building blocks QKD, PQC, and optionally classical are input to some kind of key derivation, and the shared authenticated key is given as output here. And as you've seen in the slide before, the Muckle uses pre-shared keys for authentication. There was a sentence in the paper also that it should be possible with PQC signatures, and they were saying essentially, yeah, one could look at it, and even the framework they provided, they also let room to include PQC signatures, but this was not shown. So we looked at this. So essentially, and we proposed Muckle with PQC signature for end-to-end authentication. So and we said, okay, in the beginning, you're thinking, okay, replacing pre-shared keys with signature, it might not be that hard, but it was surprisingly non-trivial. And I listed here distinguishing features. First of all, we had to slightly change the protocol style. The Muckle protocol has rather a back and forth, and then the shared key is established, but we opted for a more Sigma style protocol, meaning we go forth and forth again. And it's more kind of, you can think of how TLS is doing this. So we changed the protocol in that regard. So this is the first point. The second point is here that one can observe that to establish now end-to-end authentication with signatures instead of pre-shared keys, PQC keys are required. And this is due to the single path QKD trusted node issue. Remember that, or recall that the trusted nodes in the middle, they know the secret of the QKD, and in that regard, they kind of know a lot. The fallback here is that if we want to allow the PQC KEM to fail, since we now require PQC KEM as well for authentication, we have to rely on multipass QKD, which was not present in Muckle. But yeah, we wanted to get the same security guarantees out of that. You see on the right how this can be done. Essentially, there's a protocol on the higher layer, on an application layer, where the keys from the QKD devices are provided to the upper layer, and then the protocol, the Muckle Plus protocol is run. also in a session-based style, and particularly retaining the security of Muckle. And I want to go in a slight more detail on that, on the quantum safe security of Muckle and Muckle Plus, and particularly on the topic of forward security. Forward security is an important security feature. It's well researched for key exchange now, and it's gained also massive interest in other domains. It's now done also in a more non-interactive setting for forward secure public key encryption, or forward secure zero round trip key exchanges can be used in TLS. And so this is one of the most important features here, which Muckle and Muckle Plus also achieve. The second feature is post-compromise security. That's essentially, or loosely saying, allows a channel to heal. Yeah? And if you look on the right, there I made an example where there is a timeline you see in red. And at some point, this is the fourth dot here, at some point, all secrets of the protocol leak. Of course, you cannot gain any security at all because all secrets leak, but you can get security for past session as well as future session. And you can even get security for past or future session if QKD or PQC secrets leak. Yeah, you still got the safe session. So for earlier session, you have the forward security guarantees, and for later session, you have the post-compromise securities. We also looked at implementation and built it with a real QKD system. You can see the setup on the right. Essentially, this is also done according to the standard document by ETSI, way up on the lower end of the dotted line. You see the QKD setup with the trusted nodes and the key management system that are link-to-link connected, and above the dotted line where you're getting the keys of the QKD to the application layer, and there are also keys for post-quantum and classic. We experienced that around a key rate around 1 to 2 kilobits per second, and up to 1 second delay to fetch 256-bit keys from the QKD devices. And essentially, this resulted in that the choice of PQC signature schemes, particularly, it does not impact the performance at all. The delay comes from the QKD system that dominates even the overhead from signatures and public keys. So the takeaways here is that there's massive interest in PQC, as seen by NIST, BSI, ANSI, and also QKD. And QCI with a huge number of currently ongoing projects and also investments worldwide, and building large-scale quantum-safe networks, having in mind the end-to-end authenticity, integrity, and confidentiality is non-trivial. And that's where particularly hybrid authenticated key exchanges come in, as they hedge against various forms of future threat, particularly with strong forward and post-compromise security for the to-be anticipated quantum-safe networks. If you want to take a closer look at the details, I refer to the ePrint version, which you see here. And with that, I thank you very much for the attention.
We have time for some questions.
Hi. So, so have you only simulated this, or was the biggest network you've run Muckle Plus on?
This was not simulated. This was a network with 3 nodes in Vienna.
Okay, so it was 2 end users and 1 trusted node between them?
Exactly. Yes.
Thank you.
I have a question. If we go to a larger network, would the performance scale down proportionally?
To be honest, frankly, I don't know. This has to be tested. We are not in that stage yet.
If there are no other questions, we can thank the speaker.
Thank you.